All right. If I was able to convince you why you should learn linear algebra for machine learning, let's go ahead and put our feet in the water. Let's start with vectors and vector operations. Let's briefly discuss how they can correspond to data, and let's do some math as well, like very simple, very simply. So vector, but I would like to start with our notation actually. What is scalar, what is vector, what is matrix? So we are doing machine learning and data science, right? So like let's say we're dealing with image data, and these images are composed of what we call as pixels. So like eventually they will be boiled down to small parts, what we call pixels, and these intensities are the actual information that makes you record your images, or recognize, or do something fancy with it, or generate, right? So these pixel intensities show how what the color of it, what the color is, what the intensity, the darkness of it, and these pixel intensities we can deem for our purposes. Obviously, we will go back and forth with math and application. So for our purposes, pixel intensities are scalars. So we will denote scalars with lowercase letters, just like in algebra, normal algebra, lowercase a, b, alpha, beta. But as I mentioned, a bunch of them. So we will we will develop operations to process a bunch of these pixel intensities you can deem as patches of your image, right? So this bunch of a set of scalars represented in a column is deemed as a vector in our representation. I will, however, if some of you are thinking about vectors are familiar from physics, yes, all of the physics properties of vectors also exist in data science too, but I'll get to that. This is just we're talking about the basic notation. Right, so the vectors, we will represent vectors as typically x and y, but bold case. So vectors have multiple elements. So x of I represent the ith element of this vector. So for example, the x of 2 is 2 in this vector. And bunch of these column vectors create matrices. So this two-dimensional elements in linear algebra, we call them a matrix. And matrices are represented with uppercase letters, and obviously they have two scripts, two dimensions. Of course, we will eventually deal with higher dimensional matrices, which like 3, 4, 5, 6 dimensional matrices, and we will call them tensors, but let's not worry about that yet. So before I move on to these applications, operations, I would like to go to my notes and then write down some of these vector operations, right? So let me go and open up. So I promise this is going to be like super simple, and you'll probably be underwhelmed by this, but by the simplicity of this. But let's just for the sake of completeness, let's cover the parts that are important. So like about a vector, so we say vectors, right? Vectors. So this vector, we discussed vectors to be column vectors. Let's take one vector to be, let's say, 1 and -2, and these vectors have their indices and etc. So if I were to do the first operation, vector and scalar multiplication, let me delete this part and have the title scalar multiplication, right? Scalar multiplication, and let me denote my vector to be with a variable. So not that I have this underscore here to make it different from a scalar. Normally in math, in papers, we denote vectors with boldface, but since I cannot do the boldface here, so if I were to, like, if I represent A to be a scalar, and let's make A to be 2, and if I were to make AX, it is doing nothing but multiplying each and every one of the elements of the vector with this scalar. So like what I will have eventually is 2 times 1, 2, -2 times 2, -4. So this is going to be my scalar multiplication. Similarly, if I call B to be a negative number, I can have bx to be -1 and 2. So that's another vector. Apologies for the fat vector here. So the second operation is, as I promised to you, there are only 2 actually, addition, right? Matrix addition. So that's not so difficult also. So like right now I'm gonna define 2 of them. So I have x, let's call this 1, -2, and y to be -2 and 0. So if I were to make x plus y, you guessed it, I just add the 2 elements, the corresponding elements here, this element to this and this element to this, and I add them up, right? So like it's what's going on, 1, -2, -2, 0, so I get -2. So that's matrix addition for you. Well, I said matrix addition. It's not technically wrong. Every vector is a matrix, so I'm gonna let me go ahead and call it vector addition. So I have 2 of them, right? Scalar multiplication and vector addition. So let's go back to our presentation and get some intuition of what these operations are doing. All right, let's go to the topic. So we covered our notation. So vectors, as I mentioned, so when you remember vectors from physics, right? So vectors, as I mentioned, there are multiple numbers in a list, a column list. So I choose 1, 2, but this vector is very similar to your vector in physics. So like when you have 2 vectors here, you can deem them as like the arrows, as you remember from physics, or more importantly, they are not necessarily arrows or list of numbers. They are points on a plane, right? They have their own relationships between the 2. Like if you remember from physics, we were talking about some angle of the vector from the x-axis. Yes, this angle exists, and vector's magnitude from the origin. Yes, this exists, and we will be interested in the angle between vectors, because the moment that we start taking vectors to be data points, the angle between them is going to start telling us some information. So we discuss scaling a vector, right? Scaling a vector Very boring. We just multiply every element with the same number. But what happens when I scale this vector 1, 2 with some a? So if I scale this vector, you see this red arrow for changing for different a values. So you see that when I scale a vector, I'm not changing its angle, but I'm only changing its magnitude. So, and we just established that vectors are also data points, right? So this one data point, one vector, one word, one image, one data that you are going to deem if abnormal or not, whatever you're processing, is some point on the space. And when you scale, when you are talking about a times x, your a, you see how this a is moving. So a is moving. A is a bunch of data points. A times x is a bunch of data points on the direction that x points to. So keep this in mind, because the points of ax, for all points of a, they actually form a line, right? So the line, this word is the word that gives its name to our class of linear algebra. And we discussed addition. When we add two vectors, we do nothing. So I have 1, 2, negative 2, 1, negative 1. When we add them, we just add every single element and we get our combined vector. So our combined vector is composed of their kind of compound, right? So this is not interesting, but when we think about the matrix addition as a subtraction, right? So we can actually subtract one vector from another. So like similarly, subtraction is an addition. I didn't lie to you. The only two operations are addition and multiplication, scalar multiplication and vector addition, and everything is going to be starting from that, right? So like if I subtract, I see the difference, I get a vector, which is the subtraction of the two. And see, I'm going to now change the yellow vector, the one that is subtracted from x, for different values. And if I keep rotating this, if I keep changing the yellow, you see that the subtraction vector becomes the red one can't take any number. The reason I'm doing here this is to get to, if I choose one yellow y vector to be the same thing as the x vector, I can get the subtraction to be 0. Notice that the only reason of this slide is to show you that there exists a 0 vector. So it's different from 0, right? It's different from number 0. So we're talking about a 0 vector here. All right, in the next video we will talk about linear combination. We're going to combine multiplication and addition. We're going to get our one of the most important concepts in linear algebra, which actually takes its name from linearly combining vectors.